Welcome to our deep dive, and let me tell you, this one is heavy, literally.
Oh, it is.
We're tackling James Clerk Maxwell's A Treatise on Electricity and Magnetism, Volume 2. I mean, just holding this book,
Yeah,
you
yeah.
feel a little bit smarter,
I
right?
mean, absolutely. A little intimidated, but yeah.
Intimidated for sure,
Yeah.
and dense, let's be honest.
Very dense.
So we're going to sift through all the serious science here, and we're going to pull out the coolest, most mind-blowing stuff about magnetism, and especially how it connects to electricity.
Yeah. It's fascinating to see how scientific thinking evolved, through experiments, through debates, and how we got to where we are now.
Absolutely. So Maxwell, right off the bat, gets really practical. He's talking about how magnetism actually makes things move, which is, I think how most people think of magnets.
Right.
But even when he's talking about, like, breaking a magnet in half, there's this deeper truth hiding there.
Yeah, and that you always have a dipole. You can't just isolate the north or the south,
Right.
no matter how many times you break a magnet.
It always comes in pairs.
Always comes in pairs.
Does that mean that the stuff that makes up magnets is, like, everywhere, but it's just arranged differently?
That's where the concept of magnetic domains comes in.
Okay.
So imagine each tiny region within a material has like a mini north and south pole.
Okay.
And in most materials, these are randomly oriented and they just cancel each other out. But in a magnet, they're all lined up.
So it's not just that the stuff is there, it's that it's, like, organized.
It's organized,
Okay.
yes. And that's what gives it its power.
Gotcha. So that organization, those little, like, mini magnets all lined up, that's what makes a magnet a magnet.
Exactly.
Okay, now to help visualize this, Maxwell introduces this concept of lines of force, which, sounds very Star Wars-y.
It does.
But what are we really talking about here?
We're talking about the magnetic field and how it's visualized. So the lines tell us both the direction and the strength of the field. You've seen those diagrams where you put the iron filings around the magnet.
Those are so cool.
Right. And you get those lines. That's what we're talking about.
So those are literally the lines of force.
Those are literally the lines of force.
It's amazing.
Yeah. And how the closer together they are, the stronger the field.
I see. Okay, so the lines get all squished together where the magnet's really strong.
Exactly.
Okay, now I noticed that Maxwell makes this distinction between magnetic force and magnetic induction. And apparently things get kind of weird inside the magnet.
Yes, because outside the magnet, they are the same.
Right.
But inside, magnetic induction is different.
And why is that? What's going on inside?
Well, magnetic induction tells us how a material amplifies the magnetic field it's exposed to. So inside a magnet, the magnetic field is amplified by the magnet itself.
Okay, so some materials are, like, better magnetic amplifiers.
Exactly.
So that explains why some things are, like, super attracted to a magnet and some things are just, like, kind of meh.
Exactly, yeah. And this brings us to one of the most fascinating aspects of Maxwell's work, where he delves into Faraday's discoveries on induction, electromagnetic induction.
This is where things get electrifying.
Yes.
Literally. Because moving magnets can actually create electric currents in nearby wires, which, that's like, hello, generators.
Absolutely. And it also works the other way around.
Wait, so electric currents make magnetic fields too? So magnets can make electricity, and electricity can make magnets.
Yes, that's exactly right.
It's like a loop.
It is.
My mind is officially looped.
It's a beautiful loop, isn't it?
It is.
And this leads to the question, is the Earth itself a giant electromagnet?
Wait, the Earth's magnetic field, the thing that makes compasses work and protects us from solar wind, is that? That could be created by, like, electric currents inside the planet.
That's one of the leading theories.
Wow. Okay, I need a moment to process this. We've gone from, like, simple bar magnets to the Earth's core in, like, 5 minutes.
I know. It's pretty amazing. And we're just getting started.
This is why I love these deep dives. You never know where they're going to go.
You never know. And now get ready for your mind to be truly blown, because we're going even deeper. Maxwell didn't stop at explaining the Earth's magnetic field. He actually delved into how these fields are mathematically represented and introduced something called vector potential.
Okay. I got to be honest. Anytime anyone says mathematical representation, a part of me wants to, like, run and hide. But I trust you to guide me through this. So what is vector potential? And why should I care?
It's not as much about the math, but like the big idea behind it. Vector potential isn't just a trick. It points to something really profound about magnetism. Like, instead of just thinking about forces between objects, we can think about magnetism as this fundamental field that permeates space.
Okay, so we're not just thinking about magnets like attracting or repelling each other, but we're thinking about this underlying magnetic field, this vector potential stuff.
Precisely. It's a shift in how we think about magnetism as a property of space itself.
Okay, and this leads to some pretty practical applications.
It does. This mathematical framework allows us to calculate magnetic fields with incredible accuracy. And this precision is crucial for the tech we use daily, like motors, speakers, MRI machines.
Okay, so these equations that frankly make me want to take a nap are actually the secret sauce behind a lot of important technology. I'm starting to appreciate math a bit more, even if I don't get all the details.
And Maxwell goes even further. He discovered that a changing electric current in a wire creates a changing magnetic field around it, which then creates an electric field that opposes the original current.
So the wire is basically fighting the current flowing through it.
Well, it's not about being unproductive. Think of it more like the push and pull of electromagnetism. We call this self-induction. And it's crucial for how electrical circuits behave.
So understanding self-induction helps us design circuits that work correctly and efficiently. Are there real-world examples of this?
Transformers, for example, use self-induction and help us transmit electricity over long distances.
Oh yeah, so self-induction makes transformers work, and transformers make the modern electrical world possible.
And speaking of real-world stuff, Maxwell wasn't just about abstract math. He wanted to measure all of this.
Oh yeah, this is where we get all those, like, cool instruments, right?
Exactly. And these instruments help us connect theory with the real world.
Yeah, it's so cool to see those connections. Like, I remember using a galvanometer in high school. It was so cool to see the needle jump when we completed the circuit. Did Maxwell invent any of these devices?
Well, he was instrumental in advancing measurement techniques. One cool example was using a ballistic pendulum, that thing we use to measure the speed of bullets, to measure electric charge.
Wait, a ballistic pendulum for electricity? How does that even work?
He found an analogy between the energy of a swinging pendulum and the energy stored in a charged capacitor.
That's brilliant. It's like he was seeing connections between different areas of physics and then making something new to measure this stuff.
Absolutely. And he made a huge discovery connecting the ratio of electrostatic to electromagnetic units of charge.
That's the one that hinted at the connection between electricity magnetism and the speed of light.
Got it. By measuring this ratio very carefully, scientists found it was equal to the speed of light.
Whoa, so they were basically measuring the speed of light using electricity and magnetism.
It's like using different languages to describe the same fundamental truth about the universe.
Incredible. We went from simple magnets to the speed of light. This is why I love deep dives. They take you on a journey.
And we're not done yet. Maxwell's work goes even deeper, looking into how light interacts with matter and even hints at the mind-bending world of relativity.
Okay, I'm ready to have my mind bent. Let's do it. All right, my brain is fully charged and ready to get my mind bent. You mentioned relativity. What exactly did Maxwell find that foreshadowed Einstein?
So Maxwell's equations actually work really well with Einstein's relativity, even though they came before. Like, one big thing is that electric and magnetic fields, well, they can kind of transform into each other.
Wait, what? Like, depending on how fast you're moving. So, like, I might see an electric field, but you, if you're zooming by, would see a mix of electric and magnetic.
Exactly. That's special relativity in action. There's no single right way to measure these fields. It all depends on the observer.
Okay, yeah, mind officially bent. But hold on, before we get too deep into relativity, I gotta ask. If light is this wave, this electromagnetic wave, what happens when it, like, hits stuff? Does it just go through everything?
Well, think of it like throwing a ball at a wall. Sometimes it bounces back, right? Sometimes it goes through, sometimes it gets absorbed. Same with light, but we're talking about these electromagnetic waves interacting with the tiny bits that make up matter.
So how light behaves depends on the material it hits. And I guess the type of light too, right? That's why we have things that are transparent, opaque, shiny, all that.
Exactly, and Maxwell's equations help us understand all of that. How light interacts with the electric charges in a material.
Wow. It's incredible those equations can explain so much, from rainbows to lasers. But are there things they can't explain?
Well, every theory has its limits. Maxwell's equations are amazing for the big stuff, but when you zoom into, like, the atomic level, things get fuzzy. We need quantum mechanics for that.
So it's like having different levels of zoom, right?
Right.
Maxwell gives us the big picture, but quantum mechanics is for that super close-up view.
perfect analogy. And even though quantum mechanics gives us a more complete view, Maxwell's work is still super important. Like, it's the foundation for radios, smartphones, MRI machines.
It's mind-blowing how one person's work done so long ago can still have such a huge impact. But it's not just about tech, right? How did his theories change how we view the universe, like big picture?
Well, before Maxwell, electricity and magnetism were like totally separate. He showed they were two sides of the same coin connected, a big step towards a unified view of the universe.
A theory of everything. We're thinking about that thanks to Maxwell. That's pretty awesome.
Absolutely. And he revolutionized how we see light, too, showing it was an electromagnetic wave, explaining how it acts, and this is cool. It opened up the possibility of other kinds of electromagnetic radiation we can't even see.
Whoa, so radio waves, microwaves, X-rays, all that. Maxwell's theory kind of predicted them, even though he couldn't detect them back then.
Exactly. It's like he gave us a map to discover these unseen parts of the universe,
Yep.
and then we built the tech to actually use them, leading to radio, medical imaging, satellites, all that.
This has been an incredible journey. I feel like I've only scratched the surface of this whole world of magnetism and
The
electromagnetism.
deep dive is just the beginning. Maxwell's work is still inspiring scientists today, making us ask even bigger questions about the universe.
Well, I'm definitely feeling inspired to keep learning and exploring. Thanks for being such a great guide.
My pleasure. Anytime. Keep asking those questions.